All right, there's two kinds of gas law questions. This lecture's about how to solve a gas law problem that you see in a test using your gas law equations. We've got our gas laws given to us here. I'm going to go through this little paper showing you the different laws and how to use them. Basically, there are two kinds of laws in a gas law question. There are where there's a changing system, where you start with one system of a gas and it changes. Maybe the temperature changes, maybe the pressure changes, maybe you change how much gas there is. And your job is to predict one of the variables after the change. And there's lots of those. This top one's called the combined gas law. It's very useful. It's actually all of these mixed up together. These are all of the individual gas laws that the chemists figured out. Then they combined them and found this combined rule, which we'll be using. Then there are static systems. They're systems that are the same. The first one's all about partial pressures. If you measure the pressure of each gas, that's how much pressure each gas is exerting on the container. The total pressure on the container is if you add them all up. It's that simple. So if you've got three gases, each with a pressure of, say, 1 atmosphere, all in a pot together, they add up to 3. Simple. So if you're just talking about pressures, you just add them up. Then we've got the ideal gas law. PV equals N times R times T. That's pressure times volume is the same as the number of moles times the gas constant times temperature. And we'll look at that in a moment. But that's another static system. Nothing's changing. Whereas over here we got ones and twos. We got a before and after. So let's look at these letters. P for pressure, V for volume, T for temperature, N for number of moles. If you don't know about moles yet, that's okay. You'll learn about them. They're basically a way of counting atoms. Pressure we measure in different ways. Atmospheres, kilopascals, kPa, and millimeters of mercury, mmHg. You want to be able to recognize if you're looking at a pressure by looking at the units after the number. Same goes for volume. It might be in liters, milliliters, centimeters cubed. Temperature, degrees C. We don't use Fahrenheit in science, but in gas laws we actually use another temperature scale called Kelvin, K. I'm going to tell you about that in a moment. And then the number of moles. So let's look at that temperature. We use Kelvin, otherwise it doesn't work. It doesn't work because zero is in the middle, and that doesn't work for a proportional set of relationships like these gas laws. If we look at the Fahrenheit scale, if you're familiar with that, we know that water freezes at 32 degrees Fahrenheit, it boils at 212, and if we go all the way down to the very coldest things can be, this is when the atoms actually stop moving, because temperature is related to how fast the atoms are moving. If they actually stop, it's minus 460 Fahrenheit. In centigrade, which is what we usually use in science, water freezes at 0 and it boils at 100, and things stop moving at minus 273 degrees centigrade. Now the Kelvin scale is, as I said, for working out proportional gas relationships, you need a zero-based scale. So at that very coldest temperature, nothing can ever go colder than this. Once the atoms stop moving, then they're as cold as they can be. That's 0 Kelvin. Water freezes at 273 and boils at 373. So you see, to get from centigrade to Kelvin, we add 273. That's important. Wherever you see a question where the temperature's in centigrade, C, add 273 to convert it to Kelvin, or you'll get the wrong answer every time. So let's look at this combined gas law. This looks busy. Read from the top. P1 times V1 divided by N1 times T1 equals P2 times V2 divided by N2 times T2. So if you multiply and divide before and afterwards, they're the same. I think of this as kind of your self-service gas law, because you can answer any of those questions using this law, and you don't need the other ones. You just use what you need, and cross out what you don't need. So here's an example. At the start, we got 5 liters of gas at 273 Kelvin, right? Kelvin. So we know at the start, that's the ones. V1 is 5 liters and T1 is 273 Kelvin. That's at the start, the ones. That changes, because the question is how many liters will it take up at 373 Kelvin. So we've heated it up, it's hotter now. So this is the 2s, the finish. V2, we don't know, that's the question. T2 is 373. So we've looked at our word problem, we've listed our variables, now we look at our law. We've not got any pressure, so we cross it out on both sides. We're not going to use that. We're not using the number of moles either. And now we're ready to go. And in fact, this is the same equation as is on our formula chart. We just crossed out what we didn't need. And now we plug in our numbers. So the V1, the 5, goes on up here. The T1, the 273, goes down here. And then for the finished side, the V2, we don't know, so I put in V. And the 373 goes in here for T2. And now it's just algebra. Remember I said it was simple algebra? We had V divided by 373, so we've got to do the opposite to both sides. So we're going to multiply both sides by 273, and we can solve for V. So that was all of the changing systems. Now in a static system using the ideal gas law, PV equals N times R times T. R is the ideal gas constant. This is the number that makes the proportion work. And we've got 3 different numbers because we can measure pressure in 3 different ways. We can measure atmospheres, kilopascals, millimeters of mercury. And so there's a different number for each one. It's just another thing you've got to remember to check. So here's the question. What is the temperature of 2 moles of a gas if it occupies 4 liters at 3 atmospheres of pressure? So I read through it, and as I read, I underlined temperature. I don't know what that is, but that's going to be my T. I've got 2 moles. That's N. Of a gas if it occupies 4 liters. 4 liters, that's a volume. At 3 atmospheres of pressure, that's a pressure. And then I'll list them all out. Now, what's R? We're dealing in atmospheres. So, atmospheres. So it's 0.821. So now I've listed everything I need. I write out my formula. P 3, V 4, N 2, R 0.821, T don't know, T. And then I just solve it. It's just algebra. I'd simplify it first. I'd multiply the 3 times the 4 and get 12. 2 times 0.821, 1.642 times T, and then divide both sides by the 1.642. Answering a question. So, you've got a gas problem question in front of you. What do? First, is it a changing system or is it a static system? Is there a start and a finish? If it's a static system and everything's the same all the way through, it's either the ideal gas law or a partial pressure question. So find the variables. What have you got? Find your equation. Which one are you going to use? Make sure your units are okay. Is the temperature in Kelvin? Which R are you going to use? Write it all out, then solve it. Now, if it's changing, find the start and the finish. Sometimes that's difficult. Imagine a story. Find the start and the finish. Find the variables, write them down. Check your units. Is your temperature in Kelvin? Then cross out, then write down your combined gas law. Cross out the units you don't need. Insert your variables and solve it. Take it one step at a time.